Looking at note packet number 4, before we move on, there are some terms we want to talk about really quickly that you may or may not know what they mean. A variable is a placeholder in a math sentence. For instance, if you have a math sentence like this, x would be the variable. It's holding the place for something to be plugged into it. An expression is a math sentence. Does it have an equal sign? It can be simplified, not solved. Again, this is an expression. An equation is a math sentence set equal to another math sentence. For instance, you could have 2x plus 5 equals 11. That is supposed to be solved. You solve an equation. So again, just to recap, expressions can be simplified, equations can be solved. Also, we are going to just go over real quick the area of a square. Remember that squares have 4 equal sides. They also have 4 right angles. If you're looking for the area of a square, area of any two-dimensional shape that is a rectangle or a square, you multiply the sides. So this would be side times side, or side squared. If you had a cube, this is when you take a square and you make it 3 dimensions. So if you were going to look for the volume of a cube, the volume would be multiplying the base times the height times the width, which is s cubed. Another notable thing to say is this, because this was something always confusing to me growing up. If you were asked to find the area of a square that has labels on it, and you're multiplying the sides, you also multiply the labels. So if you say 2 times 2, that's 4, but inches times inches is inches squared. Usually the exponent implies something about the dimensions you're looking at. That's a two-dimensional shape. You have a 2 in the exponent spot. That is not something that's a coincidence. If you were doing this again with a cube, and I had like 3 centimeters, and all of the edges are 3 centimeters, the volume of it would be 3 centimeters multiplied by itself 3 times. 3 times 3 is 9 times 3 is 27, but when you multiply centimeters by itself 3 times, that's centimeters cubed. Looking at the next one, looking at the perimeter of a rectangle, you can find the perimeter pretty much of any shape that is some kind of polygon, which means that it has sides and corners of some shape. The perimeter is the distance around a figure. Usually you can think of this as like a lap. If you have a soccer coach and they want you to run a lap, they want you to run the perimeter of a field. If they wanted you to run the area, well, that would be really crazy because you'd be running a lot, right? So we have an equilateral triangle, and it has a side length of 2 feet. And if you were to find the perimeter of this, the perimeter would be the 2 feet plus 2 feet plus 2 feet, because an equilateral triangle has all sides that are equal. That's 6 feet altogether. Notice that I didn't say cubed. I didn't say feet cubed because I'm adding feet to feet. I'm not multiplying. So if you were going to express the perimeter of the following, this one has s's as a side. So the perimeter would be s plus s plus s, or you could simplify that and say 3 s's. What if you were asked to find the perimeter of the above triangle if the side length was increased by 4? That would mean that, I'm going to change the color of my pencil for a second. That would mean that you were adding 4 to all 3 sides. And so you would have s plus 4 plus s plus 4 plus s plus 4, which is 3 s's And 4 plus 4 plus 4 is 12. If you have Q quarters, D dimes, and P pennies, write an expression describing how much money a person can have at any given moment. Okay, so a quarter is worth 25 cents, right? For every quarter, you have 25 cents. So I'm going to put that next to Q. And then if I put a number in for Q, that describes how many quarters I have. Next to dimes, I would put the 10 cents. And pennies, 1 cent. Not too bad, right? This can be confusing, though, if you don't go over it and look at it and realize what you're doing. If you were really, truly looking to figure out how much a pile of change is, you would count up all the quarters, all the dimes, and all the pennies, and multiply the quarters by 25 cents, and multiply the dimes by 10 cents, and multiply the pennies by 1 cent. So this is something that you will probably see somewhere on an assessment. Okay, so let's talk about BAC. BAC stands for blood alcohol content. Something that I didn't realize in the past, but I realize now, is that these are expressed as percents, right? So if you have a blood alcohol content of 0.018%, that means less than 1%. It really, truly is. I always thought that this actually was the decimal version and this meant 1.8%, but that's not true. These are actually the percents. And hopefully you know the legal limit for driving is what, right now, 0.08%. And, you know, some certain point, you're going to be not alive anymore if you get past a certain percentage and you have alcohol poisoning and whatnot. So this table is actually based on like a 200-pound person. So it's not for everybody. You know, everybody has different types of resistances to levels of alcohol depending on their body weight and the frequency that they drink. But this is the table that's describing it. According to this table, N, which is up here, represents the number of drinks. Can N be 0? Can you have 0 drinks? Yes. Can N be -2? Can you have -2 drinks? I'm going to go ahead and say no. I always have the person that talks about, well, if somebody's vomiting, well, if they're vomiting, they needed to start off with something in their stomach, so we're not going to go there. According to the table, B represents blood alcohol content. Blood alcohol content. Can your blood alcohol content be 0? Yes. Can your blood alcohol content be 100? I would say no. And the reason I'm saying that is because we have to look at the context of the problem. In the context of this is if your blood alcohol content is 100%, then you are DEAD. So let's just say no. We also have this information expressed as a table with points that represent every situation we have up here. Looking at this in a table is also kind of helpful because you can kind of see the relationship is increasing, not a surprise. But this table also does this other thing that talks about, brings to light the idea of having an input variable and an output variable. The input variable is the effector, and the output variable is the affected. So the kinds of things that you have to think about are what causes the other to happen. Does the number of beers you drink affect your blood alcohol content, or does your blood alcohol content affect the number of beers you drink? We would say the number of alcoholic drinks is the input because that's the effector. So in this case, we're going to say number of drinks is the input variable, and the BAC is the output variable. It's really, really easy to be able to tell what the input and output variable is if you're looking at a graph, because you always, when you're graphing something, put the input variable on the x-axis and the output variable on the y-axis. So that's a thing. So let's take a look at a different scenario. This one is dealing with Medicare expenditures over a certain amount of time. So if you were asked to identify the input and output variable in this situation, you can just go blindly with that rule that the input variable is the x-axis label, and that in this case is year. The output variable is the y-axis label, and that is spending in billions. One thing that is hard is you'll have a lot of relationships that you look at and you're trying to graph it and look at it mathematically, and you're looking for input and output variable, and you're looking for what the effector is. And so this one would be kind of confusing because time doesn't always it's not always looked at like it's the effector, but if you ever have time involved, it always goes on the x-axis. So that's interesting. Use the graph to estimate expenditures for the following years. 1980, you would follow this up and over to estimate, and I would say maybe 80 billion. I'm just looking up and over. The year 2000, if I go up and over, that looks like 250 billion. And 2005, it's right here. It looks like 320 billion, possibly. I'm estimating. So my estimations could be different from yours. Estimate the year the expenditures reach 100 billion. Well, that's here. So if I go here and go down, that looks like it happened in 1986 and 1988. If you're looking for the year where expenditures reach 200 billion, again, we're following the line over and down. This happened in 1995 because it hasn't reached 1996 yet. Which 10-year period did expenditures change the least? So a 10-year period is two of these tick marks. And so if I'm looking for the least amount of change, I'm looking for where it's leveled as much as possible. And I would say that the slope of this line changes least probably between 1970 and 1980. The 5-year period where it changed the most, definitely up here. And that is between 2005 and 2010. And then last, in what time period did expenditures seem to not change at all? And so we don't really have to do a 5-year one, but I can tell you that if I look between here and say right here, these two look like, actually there's more than one. Let's go here. So we have 1996 to 2000, and then we have, let's say, 2010 to 2012. So 96 to 2000, and then 2010 to 2012.